The purpose of this video is to work through a few examples where we evaluate limits algebraically. So let's begin with the limit as x approaches 2 of x cubed minus 8 divided by x minus 2. So we always want to begin with direct substitution. If we were to substitute in x equals 2, notice we'd have division by 0. So we're unable to use the direct substitution property. So instead, let's see if we could somehow simplify this function. And notice the numerator is a difference of perfect cubes. So we'll use the method of factoring to possibly simplify this function. So perfect cubes are going to factor into a binomial times a trinomial. And in case you need a little review on factoring perfect cubes, let's do that quickly down here. If we have the perfect cubes, a cubed minus b cubed, so it's a difference of two cubes, and it factors into a binomial times a trinomial. The binomial will be a and b. Then think about distributing. If we distribute a into the first term of the trinomial, then logically we would need an a squared there in order to obtain an a cubed. And using that same logic, if we distributed the b into the last term of the trinomial, we would need a b squared to obtain the b cubed. And that kind of helps you justify why you have an a squared and a b squared in that trinomial. And then the middle term, it's helpful to remember that that's a times b. But we also need to fill in our three signs here. And some clever teacher, I cannot take the credit, came up with the acronym of SOP, S-O-P, or some people teach it as SOAP. And that stands for same, opposite, positive, or same, opposite, always positive. Which means we look at the original sign in the perfect cube. This was a difference of perfect cubes, so it was subtraction. So the first sign is the same as that original sign. The next sign is the opposite of the original, and the last is always positive. And this is just a helpful way to help you remember your signs. And if we distributed this out, we would end up with a cubed minus b cubed. So in the case of our numerator, x cubed minus 8, we first need to determine what is being cubed. So in this case, we have x being cubed and 2 is being cubed to give us 8. So x is going to be our a value and 2 will be the b value. So setting up our binomial with the a and b, it would be x and 2. And then our trinomial will be a squared, which is x squared, a times b, which is x times 2, which we write as 2x, and b squared, 2 squared, which is 4. And then we'll fill in our signs according to the sign in the original perfect cube, which was subtraction. So the first sign is the same as that sign. The next is the opposite of that, which is positive, and the last sign is always positive. Now that we have the numerator factored, we notice that we can divide out the x minus 2 factor in the numerator and denominator, which leaves us with the limit as x approaches 2 of the quantity x squared plus 2x plus 4, which now allows us to do direct substitution. So remember, when we do the direct substitution, we drop the limit notation. So we substitute in 2 for x, 2 squared plus 2 times 2 plus 4, which will leave us with a final answer of 12. Our second example is the limit as h approaches 0 of the quantity 3 plus h squared minus 9 all divided by h. So once again, we try direct substitution, but quickly notice that we cannot divide by 0. So we will try to do a little algebra here to simplify our function. And there's actually two different approaches to this problem, and I'll show you both. So one option would be to actually multiply out the quantity 3 plus h squared. So if you distribute, and remember to do that carefully, 3 plus h squared is 3 plus h times itself. So we would have 9 plus 6h plus h squared. Then we have the subtraction of 9 all divided by h. Simplifying the numerator, the 9 subtract out, leaving us with the limit as h approaches 0 of 6h plus h squared all divided by h. Now notice the numerator has two terms and they both have a common factor of an h. So if we factor out an h, we'll be left with h times the quantity 6 plus h all divided by h, which allows us to divide out the h in the numerator and the denominator, leaving us with the limit as h approaches 0 of the quantity 6 plus h. And now we can do direct substitution. When we do the direct substitution, we drop the limit notation. So we end up with 6 plus 0, which is a final answer of 6. Now there's another approach to this same problem, and the second way of thinking about this numerator is thinking about this as a difference of perfect squares. So we actually have two terms in the numerator, and they're both perfect squares. So remember, perfect squares, a squared minus b squared, that's a difference of perfect squares, will factor into two binomials, one being a plus b and the other being a minus b. So we could, instead of distributing out the numerator, we could think of factoring the numerator since it is a difference of perfect squares. So I'm going to set up my two binomials in the numerator and factor this difference of perfect squares. So the a value is 3 plus h. So we'd have 3 plus h for the a values. And then we have a b value of 3 because 3 times 3 will give you 9. So we would have 3 plus h plus 3 and 3 plus h minus 3. It might even help you to have the 3 plus h in parentheses as a quantity so you could see that if I were to check this and multiply by distributing, 3 plus h times 3 plus h would give us the quantity 3 plus h squared. Then the outside would be a negative 3 times 3 plus h. The inside would be a positive 3 times 3 plus h. Those would subtract out. And then the last term would be 3 times negative 3, which would give us the negative 9. So let's continue to simplify those two factors in the numerator. So starting with my first factor here, 3 plus h plus 3, if I add the 3's, just leaves us with 6 plus h. And if we look at the second factor, which is 3 plus h minus 3, the 3's subtract out, so we're left with just h. So notice the numerator right now is already factored. So therefore the h's will divide out, leaving us with the limit as h approaches 0 of the quantity 6 plus h. And now we can do our direct substitution, 6 plus 0, and arrive at our final answer of 6. This next example is the limit as x approaches 0 of the square root of x plus 2 minus the square root of 2, all divided by x. So begin with direct substitution, but quickly we notice we cannot divide by 0, so the direct substitution property doesn't work right now. We need a different algebraic method. So in the previous examples, we have tried factoring. However, there's nothing to factor in this numerator. We've also tried distributing, but there's nothing to distribute either, so we need a different algebraic tool. And for this problem, that algebraic tool is multiplying by the conjugate. So quick review on the idea of what a conjugate is in mathematics. So conjugates are going to be binomials such as a plus b and a minus b. So notice how we have changed the sign of only one of the terms. And if we were to multiply conjugates, if you multiplied a plus b times a minus b, notice we'd end up with a squared minus ab plus ab minus b squared. So the ab's would subtract out, leaving us with a squared minus b squared. So we'll use this conjugate idea, and we are going to multiply by the conjugate of the numerator. So again, we're going to change just the sign of one of the terms, which means we'd multiply by the square root of x plus 2 plus the square root of 2. However, we can't just multiply by some random expression. That would completely change the value of my limit, but I can certainly multiply by the number 1. So if I multiply by the conjugate in the numerator and the denominator, then what I'm really multiplying by is equivalent to 1. So we're not changing the value of the limit. So we've got the limit as x approaches 0, and now we're going to multiply the numerators. So we have a binomial times another binomial, which requires us to distribute. So the square root of x plus 2 times the square root of x plus 2 is just x plus 2. Notice the outside would be the square root of 2 times the square root of x plus 2, but the inside would be the negative square root of 2 times the square root of x plus 2. So those are opposites, those will equal 0. Therefore, when you think about this using the old acronym of FOIL, essentially, if we're multiplying conjugates, the outside and the inside are always going to subtract out and equal 0, leaving us with just the first and the last. So continuing on, we have the last, which would be the negative square root of 2 times the positive square root of 2, which would be just a minus 2. Now, in the denominator, we're multiplying x times the quantity, the square root of x plus 2, plus the square root of 2. And I'm going to have you leave that factored. So I'm not going to distribute that in, but rather leave it as x times the quantity, the square root of x plus 2, plus the square root of 2. And the reason why I'm not going to distribute this x, I'm not going to distribute that into this quantity, is because my hope is we can eventually do direct substitution. And I can't do direct substitution now because of this x, so I'm hoping this x is going to eventually divide out. That's why I'd like to leave it factored out. Notice in the numerator, the 2's are going to subtract out, which then leaves the x in the numerator free to divide out with the x in the denominator, which is exactly what we were hoping was going to happen. So we're left with the limit as x approaches 0. Now we have 1 in the numerator, and then in the denominator we have the square root of x plus 2 plus the square root of 2. Now we're free to do our direct substitution and substitute in 0 for x, which will give us 1 divided by the square root of 2 plus the square root of 2. If we combine like terms in the denominator, that's 1 divided by 2 square root of 2. And you could leave your answer like this, or you could rationalize the denominator. So 1 divided by 2 square root of 2, we would rationalize the denominator by multiplying by the square root of 2 over the square root of 2, which would give us the square root of 2 in the numerator, and then in the denominator, square root of 2 times square root of 2 is 2, so we really have 2 times 2, which gives us a 4 in the denominator. Square root of 2 over 4. So this square root of 2 over 4 is equivalent to our answer here, 1 divided by 2 square root of 2. This last example, the function is a piecewise function, and we're trying to find the value of the limit as x approaches 1. And remember, the whole goal in this video is we're trying to compute these limits algebraically, rather than relying on a graph or making a table. So I'm not going to graph this piecewise function. Instead, I'm going to go back to my definition, which is I know that a limit will exist if the left-hand limit is equal to the right-hand limit. So because I have a piecewise function, we are going to compute one-sided limits, the left-hand and the right-hand limits, and we'll see if they are equal. And if they are, then we know that the limit exists. And if they're not, then the limit does not exist. So we'll start by computing the value of the limit as x approaches 1 from the left. Now remember, if we're approaching 1 from the left, this means we're going to consider values that are smaller than 1. So looking at your piecewise function, when we're looking at values of x smaller than 1, that means x is less than 1, which means we would be on the piece of the function which is negative 2x plus 2. So evaluating the limit as x approaches 1 from the left is the same as evaluating the limit of negative 2x plus 2. And now we can apply the direct substitution property and do our direct substitution, substituting in 1 for x. We get negative 2 times 1 plus 2. So we see the value of the left-hand limit is 0. So now we do the same thing, but this time we look at the limit as x approaches 1 from the right. So if we're approaching 1 from the right, that means we're only going to consider values that are larger than 1, which means x is bigger than 1, greater than 1, which tells me that on the piecewise curve, we're on the piece, which is the negative square root of x minus 1. So this limit will be the limit as x approaches 1 from the right of the negative square root of x minus 1. Now we can do our direct substitution, substituting in x equals 1, and we have negative square root of 1 minus 1, which is the negative square root of 0, which is 0. So if the left-hand limit is 0 and the right-hand limit is 0, then we know that the limit does indeed exist, and the value of the limit when we approach 1 from both sides is equal to 0. So my final answer is the limit as x approaches 1 of the function f of x is equal to 0.